thanks for watching. And in a previous video, I calculated the volume obtained by intersecting two cylinders. And of course, you may ask, what about the volume by intersecting three cylinders? And to be honest, I first had goosebumps about this. I thought, oh my god, it's gonna be so hard to do. Turns out it's not too bad. And so let me actually do this. So first of all, the setup. Suppose you have three cylinders. So in the XYZ plane. So suppose, for example, you have x squared plus y squared equals to 1. Behold my awesome drawing skills, okay? So x squared plus y squared equals to 1. And then you have another cylinder that says, hey, I just met you, okay? This is crazy. But here's the intersection, so calculate the volume, maybe, okay? And so this becomes x squared plus z squared equals to 1. And lastly, there's a third one, wants to join the party, which is this cylinder, which here becomes, so x is missing, so y squared plus z squared equals to 1. So if you intersect them, it's possible to visualize, but you get some sort of a blob. Let's call this E. And the idea is you want to find the volume of E. And here's the nice thing about multivariable. You don't have to visualize, you don't necessarily have to visualize the solid in order to calculate the volume, because we're given very nice formulas. More precisely, the volume, whatever it is, it's the triple integral over that solid of 1 dx dy dz. Now, you may have thought, okay, because we're dealing with cylinders, maybe it's useful to use cylindrical coordinates. And in fact, you can use this to solve this. So this is the key. So we want to use cylindrical coordinates. Basically, which says that x is r cosine of theta, y is r sine of theta, and just z equals to z. Which I think it's a great generalization of polar coordinates in R3, because the first two equations are like polar coordinates, and the last one is just the same. And the question now, of course, is, what can we say about r, theta, and z? And for this, I would say, let's focus on the blue cylinder, first of all. And if you look at the blue cylinder, well, of course, you notice that the radius is just between 0 and 1. So r is between 0 and 1. And the question is now, what about the angle theta, which goes from here? So from the x-axis to the y-axis, something like that. So this is x, this is y, and this is theta. Well, of course you can't visualize this, but if you just think of the setup of the problem, it is sort of symmetric. In particular, it is actually just enough to focus on the first octant, which is just the positive x-axis, positive y-axis, and positive z-axis. In the end, you just multiply your volume by 8, and then it gives you the correct thing because there are 8 octants. And the thing I'm trying to get at is, in this first octant, well, the angle isn't between 0 and 2 pi, it's actually just between 0 and pi over 2. Because that corresponds to 0 and that corresponds to pi over 2. So theta is between 0 and pi over 2. That said, we will do better in a second. So don't ingrain that in your mind yet. We will do an improvement. And also in that octant, well, z is greater than 0. But again, we want to improve this as well, because z cannot be like 2 or anything, because that would be outside our region. Okay, and now let me erase this beautiful picture. We actually don't need this anymore. I don't think we need it. Maybe later we'll need it, but then we're screwed. Anyway, so now I actually want to get better equations for z, because as I said, there is some restriction on z other than being greater or equal to 0 here. And for this, the nice thing is, even though we don't know what this looks like, we still have our equations. So in particular, suppose you're inside the cylinder, x squared plus z squared is 1. So x squared plus z squared is less than or equal to 1. That actually gives you that z squared is less than or equal to 1 minus x squared. And because our symmetry assumption, we get that z is less than or equal to square root of 1 over x squared, because z is positive. So on the one hand, we know that z is less than or equal to square root of 1 minus x squared. On the other hand, there's another equation involving z that we haven't used yet, which is the other cylinder. So y squared plus z squared is less than or equal to 1. In a analogous way, this gives us z is less than or equal to 1 minus y squared. So we actually given two informations. So z is less than or equal to square root of 1 minus x squared, and also z is less than or equal to square root of 1 minus y squared. In particular, z has to be less than or equal to both of them. Okay. And that's very important. That helps us to, this helps us to give an even better estimate. And by the way, you could write this in terms of cosine and sine. So that's square root of 1 minus r squared cosine squared theta, and square root of 1 minus r squared sine squared of theta. All right. Now remember what I told you before. Before I said, well, theta is between 0 and pi over 2, but we can actually do better than that. So if this is theta, it's between 0 and pi over 2. Because let's look at those functions. 1 minus r squared cosine squared, 1 minus r squared sine squared. So I'd like to remind you that at some point, cosine is bigger than sine. Namely, if you draw cosine, the graph looks something like that. And sine looks something like that. Goes from 0 to this. And in particular, there is some sort of a turning point here. Namely, at pi over 4, cosine is sine. And more precisely, from 0 to pi over 4, cosine is bigger than sine. And what this means is, on 0 to pi over 4, we're subtracting more things from z here than from here. Therefore, square root of 1 minus x squared is less than square root of 1 minus y squared. So suppose this is square root of 1 minus x squared, and this is square root of 1 minus y squared. On the interval 0 to pi over 4, indeed, square root of 1 minus x squared is less than the other function. And remember, we want to find the smallest one between the two. So in this interval, it's actually easy to find the smallest one, namely square root of 1 minus x squared. Which tells you that this becomes even easier than before. Instead of saying theta is between 0 and pi over 2, let's just assume theta is between 0 and pi over 4. Because then, we don't need to care about the other equation anymore. We just can use this equation. And notice, at least the way I draw this picture, it is symmetric. So in fact, you just calculate the stuff from theta to pi over 4, and in the end, you multiply your answer by 2 because of this restriction. and by 8 because of the octant restriction. So our actual answer is 16 times this simplified answer. Okay. So based on what I said, we can finally tackle the integral. So the volume is 16, again 8 times 2. And then, from what I said, assume theta is between 0 and pi over 4. Well, the radius, as before, is between 0 and 1. And lastly, what about our z? We assume z is between 0 and square root of 1 minus x squared, which becomes square root of 1 minus r squared cosine squared theta. And respect the order, so this is dz, dr, d theta. And remember, because of cylindrical coordinates, you need this extra factor of r in the Jacobian. And this factor is actually very useful. Otherwise, the integral turns out is impossible to calculate, at least very hard to calculate. But now you'll see it's much easier. And the nice thing is, here's where the thinking stops. We took this complicated geometric problem and wrote it down as an integral, and now we just have to calculate that integral. So this becomes 16 times integral from 0 to pi over 4, integral from 0 to 1. This doesn't depend on z, so it's just a constant r times b minus a. R times 1 minus r squared cosine squared theta, dr d theta. And now let's evaluate this. And as I mentioned before, without the r, it would have been very complicated, but now it's not too bad. So, first of all, the square root, just write it down as 1/2. And here comes a crazy integral extravaganza. So integral from 0 to pi over 4. Okay. Now, the 1/2 becomes 3/2, right? 1 minus r squared cosine squared theta, 3/2. To remedy this 3/2, we have to multiply by 2/3. Now, if you differentiate this, you get this factor of -2. To remedy that, you multiply by -1/2, and actually ran out of space, but moreover, you have this constant cosine squared theta. Well, you have to divide by that constant. And by the way, we're okay because theta is between 0 and pi over 4, so no singularity here. And we evaluate this monster from 0 to 1. And you'll see I want to say it's not that bad, but it's okay. It's something you do on a Monday morning or something, okay? So, we're on the final. Maybe I should ask that on the calculus final. So that becomes -16/3, okay? And then, if you plug in r equals to 1 here, you get 1 minus cosine squared, integral from 0 to pi over 4. 1 minus cosine squared theta to the 3/2. And you divide by this cosine squared theta. And you plug this in at r equals to 0, so you get, I guess I pulled out the -1/2 out, so you get a minus 1 minus 0 squared cosine squared, so 1. So 1 over cosine squared theta d theta. Let me just double check. So this, yeah. And now let's simplify this whole garbage, okay? So, well, it's kind of beautiful because 1 minus cosine squared, that's sine squared, to the 3/2 becomes sine cubed. So minus 16 over 3 integral from 0 to pi over 4 of sine cubed theta over cosine squared theta, and then minus 1 over cosine squared is secant squared theta d theta. And well, this looks like a horrible integral, but this is also one of those standard calculus techniques. Because you have an even power of sine, you write this as sine theta, sine squared theta, and that becomes sine of theta 1 minus cosine squared of theta, which becomes sine of theta minus sine of theta cosine squared theta. So we get minus 16/3 integral from 0 to pi over 4. Whatever I said here, so sine of theta minus sine of theta cosine squared theta over cosine squared theta. This, of course, is tangent, but let's just evaluate everything at the end. Okay. And again, this looks horrible, but we can simplify this. So, this is minus 16/3 integral from 0 to pi over 4 sine of theta over cosine squared theta minus sine of theta, and again minus secant squared theta d theta. And this now turns out you can evaluate this. It's not too bad. I feel like for the last 20 minutes I'm like, it's not too bad, it's not too bad. I'm just making excuses. So this, if you like, you could either just use a u substitution, or notice it's the antiderivative of, let's see, yeah, minus 1 over cosine theta. Nope, the other way around. Because it's the antiderivative of 1 over cosine theta, because if you differentiate this, you get minus 1 over cosine squared theta, and if you differentiate cosine of theta, you get a minus sine of theta. So this is correct, and then minus sine becomes plus cosine. And then minus, now you can rejoice, it is tangent of theta, and that's from theta equals to 0 to theta equals to pi over 4. So, you're left with the following. Minus 16/3 of cosine of pi over 4, that's square root of 2 over 2, or if you want, 1 over square root of 2. So if you take 1 over cosine of theta, this becomes square root of 2. And the tangent of theta, that's minus 1. And the tangent of pi over 4, it's 1. So with this, it's minus 1. And then you do minus everything, but with 0. And cosine of 0 is 1, so you get minus 1, minus 1, minus 1. Yes, okay. And then let's simplify this a little bit. So it's minus 16/3 times 3/2 square root of 2 minus 3. And well, let's simplify this more. So the 3's cancel out. So if you want minus 16/3, first pull out the 3, and in fact pull out the 3/2, and you get square root of 2 minus 2. The 3's cancel out here. This becomes minus 8. So it's minus 8 times square root of 2 minus 2. And last simplification, that is 8 times 2 minus square root of 2. Ta-da! So we have indeed calculated the volume of intersection between 3 cylinders. And by the way, if the radius were r, here we assume the radius was 1. If the radius were r, then there would be an extra factor of r cubed. So I think this is pretty neat. We couldn't really visualize this object, and it was very hard to describe it geometrically, but just using those math equations and a little simplification, we're actually able to transform this into an ordinary integral. And so, if you like this and want to see more cool math, please make sure to subscribe to my channel. Thank you very much.